Dear students, in this session we will see about an important engineering application device, namely the Venturi meter. So the Venturi meter looks like the diagram what I have been shown here. It consists of an inlet pipe and a convergence section you can see, and a throat section, a minimal cross section area, and a divergence section and a pipe. So the Venturi meter is a device. Can anyone guess what the use of the Venturi meter may be? Why this Venturi meter we use? The flow is happening through a pipe. Now we are making the flow to get converged in the convergence section. Then it follows through a throat region. Then once again it gets diverged and once again follows along the normal pipe. Okay. So what is the aim or the use of this Venturi meter? If this section is not there, how the pipe will be? The pipe will be just like this, isn't it? The pipe will be just like this. The flow will happen from the left to right. But here we made some changes consisting of convergent portion, throat and a divergent portion. So why they made like this? Once they made like this, it's called as Venturi meter. So what may be the application of this one? It is to find the discharge. It is to find what? The discharge. What do you mean by discharge? What do you mean by discharge? How much amount of fluid is passing per second? How much amount of fluid is passing through this pipe per second is called as discharge. Can you think about the unit of this discharge? What is the unit of discharge? Meter per second is the velocity. Meter per second is the velocity. So discharge means capacity. Capacity means in what terms you used to tell? Liter. Very good. It is either liter per second, but liter per second is not a common term. It is a meter cube per second. It is what? Meter cube per second. So the main use of the Venturi meter is to find the volumetric flow rate. This discharge is also called as volumetric flow rate. The volumetric flow rate, the volume itself indicates what? Volume. Rate means it's per time. So the volumetric flow rate is used to be obtained with the help of what? Venturi meter. So this Venturi meter is used to obtain how much amount of mass of a particular fluid in terms of meter cube or in terms of centimeter cube or in terms of liter per second is passing. That we can get it with the help of this Venturi meter. I hope you got the application of this flow rate of this Venturi meter to determine the volumetric flow rate. Can you think about another flow rate? When there is a volumetric flow rate, there should be another flow rate. What is that? It's called as mass flow rate. It's called as what? Mass flow rate. Can you tell about the unit of mass flow rate? Here it is meter cube per second. Huh? Very good. Kg per second. Kg per second is called as what? Mass flow rate. In this device, we are determining the volumetric flow rate. Whether it is possible to find the mass flow rate? How? We don't know. Okay. So we can see, I want to move from meter cube per second. What should be my final answer? Kilogram per second. Isn't it? I have to start from, because I am going to find the volumetric flow rate with the help of Venturi meter. But I am asking you to find the mass flow rate. So what if we are doing something with this one, when I can get this kg per second? With this one. If I am going to multiply with what?
Gravity.
No, not gravity. I want the unit of kilogram per second. Now it's meter cube per second. Then what should be the denominator?
1 by meter cube.
Yeah, meter cube. So meter cube goes away. We will get a 1 by second only. But I want should have kilogram. So what is kg per meter cube? What is kg? What is the quantity of kg?
Weight.
Not weight. Mass. Weight means Newton. It is kg means what? Mass. By meter cube means?
Mass by liter.
Mass by?
Volume.
Mass by volume is nothing but density. So if I am able to find the volumetric flow rate, and if I go, this quantity is nothing but density. Why? Density equal to what? Density equal to what? Mass by volume. So once you have find the volumetric flow rate, and if you know the density of that particular fluid, if it's water means 1000, if it is air means around 1. Okay, but some other oil say its density is 850. Then you have to multiply by 850. So if I am going to multiply by the corresponding density, I will end up with what? The mass flow rate. So we can call the Venturi meter as a device to determine the volumetric flow rate. Indirectly, you will be also in a position to find the mass flow rate by multiplying the corresponding density of the fluid. By corresponding multiplying the density of the fluid. Okay, now let us go to the working principle. Now we come to know what is meant by discharge or volumetric flow rate as well as the mass flow rate. Now how this particular device, Venturi meter, is able to obtain the volumetric flow rate. That is our next step. Okay. Yeah, I will erase all those things because already we know the unit of volumetric flow rate and mass flow rate, and the use also we have discussed. Okay. The main thing from which the flow rate can be obtained is through the Bernoulli's principle. In the last session we have discussed about the Bernoulli section, Bernoulli's equation and the corresponding Euler's equation of motion. Okay. So based on the Bernoulli's equation, we will try to find the volumetric flow rate of this fluid which is flowing through this pipe. Okay. What is Bernoulli's equation? Any guess? What is Bernoulli's equation? In the last section we discussed. The total energy remains constant. The total energy remains constant. So what are the type of energy? It is nothing but the potential. It is nothing but the potential head, kinetic head, and the pressure head. So the first term will be the pressure head, P by rho g. The second term will be V1 squared by 2g plus Z1 is equal to P2 by rho g plus V2 squared by 2g plus Z2. Where this V1 and V2 are not volume but they are velocity. But they are what? Velocity. So Tarni, can you tell what this term corresponds to? Which type of energy? V squared by 2g. What can be the type of energy? Here V is velocity. Very good. It's kinetic energy. What about this one? Is it his height? Datum height. What is this one? This height is nothing but what? You take some from particular height to the center of this one is nothing but what? Is Z1. Got it? What is Z2? This is the point 2. So if I am going to take from here to this datum height, this is nothing but what my? Is Z2. So what is this datum height? This H indicates what? Potential energy. This H indicates what? Potential energy because mgh. Because it's what? mgh. Okay, got the logic. So this is the potential head, this is the kinetic head, this is the pressure head. This is nothing but what? Pressure head. So this, if you are going to add all the three head, it is called the total head. That total head should remain constant at section 1 and 2. So you may be worrying what is 1 and 2 because we have not explained so far. So we can see 1 can be taken before the convergent region. 1 can be taken anywhere in this domain before the convergent region, and I am making a plane, and from there I am going to tap a small tube through which this water will also flow here. So Tarni, what is the pressure here? The pressure corresponds to P1. The pressure corresponds to what? P1. And here when the flow is happening, it is going through the throat. In the middle section of the throat, you take a small tap. Okay. That tap will also be similar to the same diameter. Okay. These two diameters should be of what? Same width. Now what will be the pressure at 2? If you are going to tap the water will flow here. Okay. Which will be more? Whether this pressure will be more or this pressure will be more? This pressure will be more. Okay. So what is doing means this water is going and pushing the mercury. Whatever I have drawn in the what? This circular mark is nothing but what? Mercury. So this will push the mercury downwards, and here the mercury comes upwards here. Upwards here. So now from this mercury level, what is the rise in the mercury? That height is H. That height is what? H. Then once again the water is flowing away. It can be any fluid. In our example we are considered as what? Water. In our case we are considered as what? Water. Once again I will repeat it. I want to know how much of water is flowing per second through this pipe. That is my main aim of the Venturimeter. For this I have a convergent region, throat, and a divergent region, and I am choosing a region 1 in such a way it is well ahead of the convergent domain, and I am taking the region 2 in such a way it is coming on the throat, and I am going to tap the pressure at 1 and 2, and I am going to connect these two taps to the manometer. In the previous section we have discussed more about the manometers. Please go through if you have any doubts in the manometer. As the student told, the pressure at 1 will be more, so it will be exerting more pressure on this fluid, so the mercury will come down and it goes up. The difference in the mercury level is given by what? H. So far we have seen up to here only, and I am trying to apply the Bernoulli's equation between the section 1 and 2. What the Bernoulli's equation says? The summation of the pressure energy plus kinetic energy plus datum energy will be, or the potential energy will be the same. So which is nothing but P1 by rho g plus V1 squared by 2g plus Z1 equal to Pt by rho g plus V2 squared by 2g plus Z2. Tarni, now what about Z1 and Z2? Whether they are same or different? You see the diagram. It is in the center line only. So it is Z1 equal to Z2. The diagram doesn't show both are same, but they are the same horizontal plane. So Z1 and Z2 are same. When Z1 and Z2 will be different? When Z1 and Z2 can be different? When this Venturimeter is kept horizontal inclined, then my Z1 will be less, Z2 will be more. But now the horizontal, now the Venturimeter is placed what? In the horizontal position. So Z1 equal to what? Z2. So you please assume the diagram I have not drawn to 100% perfection. So it seems that Z1 is somewhat smaller to Z2, but it's not like that. So okay, actually the center line will pass like this. So here will come up to here. So Z1 will be equal to what? Z2. So I can strike off this Z1 and Z2. So I can strike off this Z1 and Z2. So I hope you are able to understand the diagram. Shall I erase the diagram? Yeah, okay. With your permission, I am erasing the diagram. Yes, we will continue with the derivation. Trying to apply the Bernoulli equation between the points 1 and 2, which is nothing but P1 by rho g plus V1 squared by 2g. Tarni, it is velocity or volume?
Volume.
It is velocity or volume? Velocity plus Z1 equal to P2 by rho g plus V2 squared by 2g plus Z2. As we have seen in the last diagram, Z1 equal to Z2. So I can strike off Z1 and Z2. Okay, so the expression will reduce now to only two heads. One is pressure head plus velocity head equal to pressure head plus velocity head at section 2. Tarni, what is section 2? Where the section 2 comes? In the diagram? Which region? That region is called as what? It is coming on the right hand side. That's not converging. That is the throat. That is the throat. Okay, this one is before the convergent, before the converging region. Okay, now let us feel like this. P1 by rho g minus P2 by rho g is equal to, just I am doing the mathematical work, V2 squared minus V1 squared, or V2 squared by 2g minus V1 squared by 2g. Hereafter I am not putting arrowhead, but I hope you can understand that it's not volume, it's only velocity. It's only velocity because kinetic head. Even though I am not putting arrowhead, you have to assume it as velocity. Now which one we can take common, Tarni? In this term, which one we can take common? So the denominator can be rho g. So the numerator will become what? P1 minus P2. P1 minus P2. What about this one? Yeah, V2 square minus by 2g. That's it. Hereafter we are going to do simply mathematical work. If you have any doubt, you ask me. Otherwise, just I will proceed. So can you tell what is this one, Tarni? P1 minus P2 by rho g. This will create what in the Venturimeter? What is this P1 minus P2 by rho g physically means in the Venturimeter? Imagine what is 1? The pressure is acting at the 1, 1. P2 means pressure acting at the 2. Now this difference will create what? The difference will create a flow. But what will show in the Venturimeter, the YouTube manometer? The pressure is acting at 1, 1. The pressure is acting at 2, 2. So I am going to subtract the P1 minus P2 by rho g. What does this term will indicate? How it can visualize in the Venturimeter, in the manometer? Increase the mercury level. So we can find H. We can find what? So because of this pressure difference, it will create an oscillation in the H. So this term is equal to H. This term is equal to what? H. That's what I want to tell. H equal to what? V2 squared minus V1 squared by 2g. When this H will be 0, this H will not be 0, only when the pipe is parallel, when the pipe there is no change in the cross section, then what will happen? P1 will be equal to P2, then my H will be equal to what? 0. If I assume there is no loss, loss, but definitely there will be some difference in pressure. P1 will be higher than P2, and hence this is nothing but what? Pressure head. This is nothing but what? Pressure head. Okay, because we know the formula for static pressure is what? P equal to rho g h. So what is P by rho g? It is nothing but what? Head. This head is called as what? Pressure head. Here instead of pressure we have what? Difference in pressure. Difference in pressure. I hope you got it. I hope you got the logic. So it is nothing but what? H equal to V2 squared minus V1 squared by 2g. Okay, fine. I will erase it and I will move further. So I end up here with H equal to V2 squared minus V1 squared by 2g. Tarni, can you tell what is the formula for the discharge in terms of area? In terms of area, I know discharge. What is the unit of discharge? I am going to kill you. What is the unit of discharge? Yeah, meter cube per second. Okay. So what is the? I want the formula in terms of area and another term. What will be the another term? What is the unit of area?
Meter square.
So what should be this unit?
Meter per second.
What is meter per second?
Speed.
Yeah, generally we used to call as velocity. Generally we used to call as what? Velocity. So Q equal to A into V. Generally any fluid mechanics student, is well aware of what? Q will be equal to what? A into V. Now Q will also be equal to A1 V1, which will also be equal to what? A2 V2, because the flow rate remains constant. Because the flow rate remains constant, because we assume the flow is steady. Because we assume the flow is what? Steady. So A1 V1 equal to what? A2 V2. So what I am about to tell means, I am about to tell Q1 is equal, or I can generally from this what I can tell? A1 V1 equal to what? Can I tell like this? A1 V1 equal to A2 V2. From this what is V1 Tarni? A2 V2 by A1. Can I substitute this 2 in 1? I have V1. You square it and substitute over here. And substitute over here. So what I got means, I got H equal to V2 square means V1 square by 2G. But I know that Q equal to A into V. I also know that Q will be equal to Q1 equal to Q2, which will be equal to A1 V1 equal to A2 V2. From that I am trying to find what is V1. V1 will be equal to what? A2 V2 by A1. So trying to substitute this value in 2 in 1. So what will be V1 squared then? V1 squared will be equal to A2 V2 whole squared by A1 squared. By what? A1 squared. Otherwise I can write as what? V1 squared will be equal to what? A2 by A1 the whole squared into V2 squared. Into what? V2 squared. Got it what I am telling? A2 by A1 whole squared into V2 squared. So substituting for V1 squared here. Substituting for this one. So it becomes V2 squared minus A2 by A1 whole squared into V2 squared by 2G. Now Tarni, which one we can take common in the numerator? In this numerator, V2 squared. Okay. So V2 squared will be equal to 1 minus A2 squared by A1 squared. Can I write like this? Yes, we will continue with this derivation. So in these two terms in the numerator, we can take the V2 squared as common. So it becomes 1 minus A2 squared by A1 squared by 2G. By 2G. What is your ultimate aim, Tarni? Why you are doing all this work? So in between I have some doubt. Why you want to do all this work?
Make it as meter.
We want to find meter cube per second. We want to find meter cube per second. But still we have not found out. Okay, so our aim is to find a Q. Our aim is to find what? Q. That's fine. Now, in this one, which will substitute to find a Q? I want to find Q. Which one you know in this equation? Which one you know? I will make a break. Now you tell me whether you know H. Whether you can know H by doing the experiments. You can know the value of H. Why? Because that can be seen in the manometer. Whether you know A1. Yes, we know because you know the diameter of the pipe at the intersection. Whether you know A2, yes, we know the diameter of the throat. A1 will be equal to what? Pi by 4 D1 squared. R in school will tell us what? Pi R squared. Where R is the radius of the inlet. Okay, at section 1-1. At section 1-1. Similarly, A2 will be equal to what? Pi by 4 D2 squared or diameter of the throat. R we can also call as what? Pi R2 squared. Okay, fine. Let it be these these things be the diameters. So you know A2, A1. So whether you know G Tarni? Yeah, which one you don't know? V2. Whether we can measure V2? No, we can't do. So I want to change the V2 in some other terms. I want to change V2 in some terms of some other terms. Because I know H, I know A2, A1. So that for that only we are working. For that only we are further moving on. That's good. Yeah. So from this, now what is V2? V2 squared will be equal to 2GH. What I am doing? I am writing this V2 squared. I am taking 2G to this side. So 2GH divided by what? 1 minus A2 by A1 whole squared or A2 squared by A1 squared. Both are same. Okay. This is nothing but what? My V2 squared. From this, what is V2 Tarni? Or I can even take the LCM in the denominator. 2GH divided by A1 squared minus A2 squared by A1 squared. Got it? I can take even this A1 squared to the numerator. So it become what? A1 squared into 2GH by what? A1 squared minus A2 squared. What this value now? The left hand side is nothing but what? My V2 squared. What I want to find? Not V2 squared. I want to find only V2. So from this, what is V2 Tarni? Huh? Root of all these terms. So it will be root of 2gh. I will give separately. What is a1 squared will become when I am taking? Very good. It will become a1. What are the denominator? It will become square root of a1 squared minus a2 squared. Got it? Now I am asking you. Now I know V2 in terms of a1, a2, g and h. Whether all these variables are known to you, it can be measured. So now you can get V2. Now you can get what? V2. Your problem is solved or not? Yeah, V2. But our aim is not to find V2. Our aim is to find what? Q. So how to find Q? You know now V2, but our interest is not to find Q, V2. Our interest is to find Q. What is the formula for Q? Very good. Area into velocity. Since V2 means it should be A2. It should be what? A2 into V2. Whether you know A2? Yes, that's fine. Good. So now you see, this is the V2. Our aim is not to find V2. Our aim is to find only Q or Q2. This is nothing but what? Q2. But Q2 will be equal to Q1 equal to what? Q. Okay, fine. So I can even call this as Q. So what is A2? A2 only. What is V2? A1 into square root of 2gh by square root of what? A1 squared minus A2 squared. Now which one you have found out? Which one you have found out? Q. What is Q? No, what is Q? That's area under velocity find. What is Q actually? What is the physical meaning of Q? What is Q is called as? Now we discuss now discharge. Meter cube per second. What is that? Discharge or volumetric flow rate. Discharge or volumetric flow rate. So we can see Q equal to A1 A2 into square root of 2gh A1 square minus A2 square. In some book, instead of capital A, it's not a general notation to give in capital letters. So most of the books they will follow A1 into A2 square root of 2gh. There is nothing wrong. Okay. Even if you put capital A also nothing wrong. But it's not a general convention to use capital letters. So most of the book use what? Small letters. Got the logic? So this is nothing but the formula for Q. This Q is called as theoretical discharge. Why is it called theoretical discharge? Because we derived through the formulas. Then thirdly, how we can find the actual discharge? This is the theoretical discharge. Why it is called theoretical discharge? Can you tell me once again? Why the discharge obtained by this formula is called theoretical discharge? Because we derived through the formula. And even though we are going to get all these values from the experiments, but still it's called as what? Theoretical discharge. But how we can measure the actual discharge? Now the flow is happening through a pipe. Is coming from inlet. If you want, I can draw like this. Okay, can you imagine the pipe is coming and is open here. What you can do? I can collect this water in a tank. Okay, this tank, let us assume this tank has a, if you want, I will put a rectangular tank. Instead of a square tank, I will put a rectangular tank. You see here. Got it? What I am doing? So I am trying to collect the water in a collecting tank. Let us say you know this area, the base area of the tank. Let it be rectangular. So length into breadth. Length into what? Instead of A and B, let us have L and B because already we have A. So it's length into breadth. Now use a stopwatch. You have a stopwatch or you take your mobile phone. And allow the water to rise for say some 5 centimeter rise from the ground. You note down the time. What will give Tarni? I am allowing the water to get filled inside the collecting tank. Now initially the water is 0 level. Now I am allowing the water to rise up to what? 5 centimeter. I am marking the time. I am calculating the time. What does it indicate? Speed is nothing but the velocity. It's nothing but what? The velocity. Now you can see here. Already you know length and breadth. Already you know what? Length and breadth. Now there is nothing but what? Area. There is nothing but what? Area of the collecting tank. Into this 5 centimeter by time also you know. Time is say some 20 seconds or something. Okay. This also you convert into meter. This also you convert into what? Meter. Then it becomes what? Meter cube per second. It will become what? Meter cube per second. That meter cube per second is nothing but what? Discharge. So you can find that discharge in a very easy manner. This discharge is called as what? Actual discharge. This is called as what? Theoretical discharge. This discharge is called the actual This discharge is called what? Actual discharge. So the actual discharge is very easy to do it. I will repeat the steps how to find the actual discharge. You have a conducting tank. You know the area of the conducting tank. If I have the area, if I am going to multiply with the velocity, I will get the this actual discharge. So what I am going to do, it need not to be 5 centimeter. You can even allow for 10 centimeter rise. You can even allow for 50 centimeter rise. But I want certain height or the corresponding time. Okay, so I know this height as well as the time. Time in seconds, this is in centimeter. These two also may be in centimeter. You please convert the centimeter into meter by dividing by the corresponding things. You will get in meter cube per second. This discharge is called as the actual discharge. This discharge is called what? The actual discharge. Now, whether the actual discharge will be more or theoretical discharge will be more. Whether this discharge what you are doing from the experiments is called as what? Actual discharge. Which will be more, Tarni? This will be lesser, this will be more. Why? Theoretically will be always higher, but actually it will be lesser. Actually it will be lesser. Okay. So we can see that the ratio of this, the ratio of the actual discharge by the theoretical discharge is called as coefficient of discharge. Is called as what? Coefficient of discharge. Whether this value will be less than 1 or more than 1, Tarnima? Whether this value will be less than 1 or more than 1? Less than 1. Q actually will be less than K theoretical, that what I told. This value will be higher, that I am putting in denominator. So the numerator is less than the denominator. So this value will be what? Less than 1. And for Venturi meter, this value of CD will range from 0.95 to 0.99. 0.95 to 0.99. Got the logic? So when you are going to do experiments in fluid mechanics lab, when you are going to coming for engineering, you will be asked to find the CD value of the Venturi meter. You will be asked you to find the CD value of the Venturi meter. You will do the experiments and calculate the actual discharge. By the formula, you will do the theoretical discharge. Then we will ask you to find what the CD. But generally, the CD value of the Venturi meter is what? Should range between 0.95 to 0.99. So you may be wondering why process is taking about CD now. So this is the theoretical discharge, but I want the actual discharge. So the actual discharge, what is the formula? CD equal to what? Q, this formula. So this is what? Q theoretical, but I want Q actual. So how to find Q actual now? Tani, can you tell me, ma? What is Q actual? From this formula. Very good. CD into Q theoretical. What is Q theoretical? This is the Q theoretical. So now CD into A1 into A2 into square root of what? 2GH divided by square root of A1 squared minus A2 squared. So this is the final formula to find the actual discharge. This is the final formula. This is the formula for finding the theoretical discharge. Along with the theoretical discharge, if I am going to multiply the value of CD, that will give what? My actual discharge. So how do you know the value of CD? By doing some experiments repeatedly in the lab. We found that value of CD should be range between what? 0.95 to 0.98 or 0.99. So I hope now all these values are measurable. CD is known, A1 is known, A2 is known, H is known. So you can find and you can enjoy the application of Bernoulli's equation in finding the discharge of flow through a pipe. When you know the discharge, you can also find the mass flow rate. Now we have found out the volumetric flow rate. I hope you enjoy the section. In future classes, we will try to solve some numerals based on this formula. Thank you.